Okay, what I would like to do now, I hope, is give you an example problem that will show what I sort of had in mind, that you would do with this little technique I just showed you. So I'm going to do that in blue. Hope this works. All right, so the problem here is we have this perfectly elastic collision between two objects with mass m1 and m2. Initially, mass 2 is stationary, so u2 equals 0 there. And we know that after the collision, object 1 is going the same direction as object 2 and is half the velocity. Okay, so this is sort of like object 1 hits object 2, 2 goes off to the right really fast, and 1 goes sort of fast, or half as fast. And for that to happen, we want to find what the ratio of m1 to m2 has to be. Okay, so here's how I would do it. Perfectly elastic collision. So we start off with kinetic energy being conserved. Okay, and what I'm going to say is the change in kinetic energy of object 1 and the change in kinetic energy of object 2 are going to be equal magnitude and opposite sign, right? I think we're all comfortable with that. Okay, so then let's see, let's go with right. So what I want to do then is go with the change in kinetic energy for 1 is 1/2 m1 times 1's final velocity squared, okay, v1 squared, minus 1's initial velocity, which is u1 squared, also squared, sorry. So this is the change in kinetic energy of object 1, and then that is equal and opposite in sign, equal magnitude opposite sign, to 1/2 m2, and then we know that object 2 started with no initial velocity, so really just v2 squared minus 0, if you want to put that in, okay, just to show every step I'm doing. What we can do then is get down to where we have 1/2 m1 times, and I could go ahead and substitute in v2, 1/2 v2 for v1 here. I'm not going to, but I could do that. So v2, actually, no, just said I wasn't going to, and there I am. So, sorry, 1/2 m1 v1 squared, actually it's not squared, sorry. I'm going to factor this to v1 minus u1, and then also v1 plus u1, right? And that's going to equal negative 1/2 m2 times, and still just v2 squared, right? There's nothing you can really factor there because it's just v2. Okay, so that's our kinetic energy equation boiled down to that point. Okay, now I'm going to do, just to be super clear, I'm going to do momentum in dark green. Yay, okay, so for momentum, which I'm doing on this side, I'm going to say the change in momentum of 1 and the change in momentum of 2 are equal magnitude, opposite sign, which means then that m1, okay, come on, just stay there. Somehow I managed to get this, no! Somehow I managed to get these drag bars here, and I don't want those. So maybe I have to shrink it a little. Shrink, there we go. Okay, so m1 times final velocity of 1, It's final velocity of 1 minus initial velocity of 1 equals negative m2 times final velocity of 2 minus, this is getting frustrating, alright, minus initial velocity of 2. Okay, so now we know again that u2 is 0, right? So I should have just put that in anyway. So I'm going to take this and take it down to below the kinetic energy 1 and just write it in. So I'm going to write m1 times v1 minus u1, okay, equals negative m2 v2. And I realize this seems kind of tedious, like it's a lot of extra writing, but do it a few times, get the hang of it, and you'll get, very quick at it. So, changing color yet again to, how about red? Okay, so let's get rid of the 1/2s, obviously, and then we can also cancel out the m1s, the v1 minus u1, the m2s, and one of the v2s. Okay, so what you get now is v1 plus u1 equals v2. Okay, so I've gone through the derivation again, but I've shown it for this specific problem. And first of all, this gets me a slightly more relevant answer. In fact, once we take this and plug in v1, it gets even more relevant. But it also helps us because because now it's more defensible. If somebody's reading it, it doesn't look like you just pulled the answer out of your butt, because you started with conservation principles and derived it from there. And your teacher will be much more likely to believe that you know what you're doing if you show them that. And anyone reading will. I mean, this is part of doing these things in physics, is understanding that you have to show where this crap comes from. You can't just say, well, I know it's right, you know? So we're going to substitute in here this V1 equals 1 half V2, and that's going to get us to the point where 1 half V2 plus U1 equals V2. And then what we know is that U1 equals, we can subtract that, so 1 half V2. Okay, so this is now getting really nice, because now V2 equals, yeah, come on, let's see. I'm going to fix my equal sign a little. Let's see, where would I go with this? V2 equals 2 times U1, and then you can go back to, say, I don't know, yeah, you can plug this into this momentum equation, and I will pick a fourth color now to do that in. How about, that's kind of like lavender, isn't it? Alright, lavender. Alright, so now I'm going to do, I'm going to substitute into the momentum equation. I'm going to go M1 times, right, and V1, alright, so actually this gets us almost all the way there, because, let me just back up and get rid of that M1. If V2 equals 2U1, then V1 equals 1 half V2, that was one of our givens, right, which equals U1. So, wow, this doesn't make any sense, does it? Why would V1 equal... What has Dr. Smith done wrong? U1 equals 1 half V2, and V1 equals 1 half V2. That would imply then that, well, maybe... Boy, that's interesting. So, let's see. Maybe I've created something unsolvable. I mean, because it looks like I've shown now that... that's interesting. So, what I wasn't trying to create an unsolvable problem, understand this. Because if V1 equals U1, then M1 times V1, well, because then M1 times V1 minus U1 is really equal to 0, and that's the change in momentum of object 1. So what I've said here is that in order for this to work, can that be right? That M2 must then be equal to 0, which means M1 would have to be infinitely huge compared to M2. Oh, you know what I have? Yeah, okay. Well, I did... How about that? Happens to everyone. So I created a problem. So that means our final answer would be M1 over M2 equals infinity. That's an infinity sign there. I'll write it here a little bigger. M1 over M2 must equal infinity. I've actually created, unwittingly, I admit, I created a problem where, yeah, no, that makes sense to me, though. I believe it. Well, there you go. I've just proved that in order for this to be true, M1 must be infinitely large compared to M2. So there you go. I hope at least you understand the technique, even if I got a really bizarre answer out of it. And hope this helps. Practice this when you're doing these perfect elastic collisions, and I think you'll find them much easier.